The central limit theorem states that the distribution of the means, or averages, of a suitable number of independent, identically distributed random variables will be approximately normal, regardless of the initial distribution. That means that if you take sets of samples from any distribution, the sample means, when plotted, will approximate a normal distribution. The central limit theorem is a really powerful concept. However, it's a concept that isn't really intuitive. In fact, Alan Turing, who is regarded as one of the greatest mathematicians of all time, proved the theorem in college because he initially didn't accept that it was true when he heard it from his professor. So if you're having trouble understanding it right now, you're definitely not alone. Throughout the video, there will be YouTube cards which pop up at the top of the screen, which link to other helpful videos which explain certain concepts. There will also be more videos and a link to my code in the description. In order to demonstrate the central limit theorem, we're going to use a binomial distribution. And the binomial distribution we're going to choose is a really simple one. It's just a flip of a coin. So if you want, you can click on the video in the card right now to get an introduction to binomial distributions. Also, in the card, there will be a video that links to an introduction to a Jupyter notebook. Right now I'm writing my code in a Jupyter notebook, so if you haven't used one before, then you can use that video to familiarize yourself. So in a binomial distribution, the variable n means the number of trials that happen per sample, and the variable p means the probability of a success. So with a coin flip, we can define a success as either a heads or a tails. It doesn't really matter in this scenario because either way the probability is 0.5, as you can see right here. And initially, just to demonstrate my first point, I made n equal 1. So that means that in each sample, the coin is flipped just one time. And here you can see that there were 10,000 samples taken. And I'll get into the code more deeply in a second, but first I just want to show here the graph. And you can ignore the axes. I'll come back to those in a second. They're just two lines. And the line to the right is the number of heads, and the line further to the left is the number of tails. And those are roughly equal. And so that is 10,000 samples of this initial binomial distribution that we made. So the on-screen distribution is obviously not normal. Now the thing you have to remember is that the central limit theorem says that an adequate sample size is needed for the distribution to approximate a normal distribution. And a sample size of 1 is not large enough. So what we can do is we can increase the sample size to, say, 250, and then we can rerun the code and give it a second. Now this looks a lot more like a normal bell curve shape. So next, let's walk through the code that is used to generate this histogram here. So in order to start our Python program, we first want to import several things. First, we're going to import the NumPy module as NP. NumPy allows for scientific computing and calculations. Next, from scipy.stats, we're going to import binom and norm. These will allow us to create binomial distributions and normal distributions, respectively. Then, we're going to import matplotlib.pyplot as PLT, which will allow us to create graphs and plots. And then, from statistics, we're going to import stdev, which lets us calculate the standard deviation. Now, NumPy also is a built-in standard deviation function, but stdev is easier because in this particular program, we have to calculate the standard deviation of a list. After defining n, the sample size or the number of trials, and p, the probability of success, we can create a list called changed_sample_mean. And I'll explain why it's called changed sample mean soon. And after that, we'll create a variable called count, which is equal to 0. Now the variable count will allow us to use a while loop. And if you can see on the bottom, at the end of the while loop, so every time the code runs, count increases by 1. And then once count is no longer less than 10,000, then the code stops running. So what this does is inside the while loop, essentially a data point is created. And so once there are 10,000 data points created, then the code will stop running. So it allows us to set the number of data points we want. So the first step we'll want to take in order to create a data point is to define a variable, I'm calling it data underscore point, as a binomial random variate. And so that takes a random variate of the binomial distribution that we created. And the two parameters of this function, binom.rvs, are n and p, which you can see up here. We've talked about them already. Then what we'll want to do is, because the central limit theorem works with sample means, not with frequencies or counts, we'll want to divide the random variate by the number of trials, so by the sample size. And this will end up giving us a number between 0 and 1 as our data point. And so you can see that data point is now defined as data point, as a previous definition of data point, so that's this definition, the random variate, divided by n. So after this, we'll want to add the data point to this change sample mean list. But first, before that, we actually want to manipulate it. And the reason for this manipulation will be explained right now. So the reason that we modify the data points is because the central limit theorem actually says exactly what is on the screen. So the square root of n, which is the sample size, multiplied by x bar of n, which is the sample mean, minus mu, which in our case is p, or the probability, which is 0.5, converges to normal distribution with mean 0 and variance sigma squared. And so because of this statement, we added to the change underscore sample underscore mean list the square root of n multiplied by, in parentheses, data underscore point, which we previously showed was the sample mean, minus p, or the probability, which is 0.5, which is also mu. So taking this step to modify the sample mean will later allow us to compare the histogram that we're going to create to a normal distribution with a mean of 0 and a variance of sigma squared. So for the purpose of this video, you can take this as somewhat of a given. But if you're interested in why it works, you can check out a link in the description. So now that you understand why we need to have a change sample mean, not just a sample mean, we can then move on, and the next step is to find the standard deviation, which in probability is denoted by sigma. And so here we'll just use stdev on our list, and that gives us the standard deviation. Then we'll use matplotlib to create a histogram. If you don't know what a histogram is, please watch the video in the card. And so we can use plt.hist to create a histogram. And then we'll input as parameters change sample mean, so that's our list. And then also normed equals true. So that normalizes the data and it gives us relative frequencies on the y-axis instead of actual frequencies. And this will be helpful later when we compare it to an actual normal distribution. Next, we'll define the minimum and the maximum x values, and we'll set the x limit. So this will create a window. And so you can see the minimum x value in the window is -2 and the maximum is 2. And then finally, we'll set an x label and a y label, and then we'll show the plot. And so this lets us create this histogram that you see on the screen right now. Once we've created our histogram, we'll next create a normal distribution which we can compare it to. So in order to create the normal distribution, we first want to create a linear space. So to do that, we'll use the function np.linspace, and that's built into NumPy. And we'll set that equal to a variable called x. And so there are 3 parameters in np.linspace. The first is the minimum, then there's the maximum, and then there's number of values. So basically what our function here does is it creates a set of 400 values that are equally spaced between xmin, which is -2, and xmax, which is 2 up here. So once we have that set, we can just plot a normal distribution. So the first parameter, will be x, so will be our linear space. And then the second parameter will be our normal probability density function. And so we can actually use x as a parameter because the middle of x is 0, just as is the mean of our desired normal distribution. And then we'll use this statement here, scale equals sigma, to set the scale equal to the standard deviation. So therefore, we've created a normal distribution here with the norm.pdf function. And then we just do plt.show to show the normal distribution down here. After that, we want to compare our normal distribution to our histogram. And so all we have to do for that is just essentially repeat the code that we wrote earlier. So we just write plt.hist. Remember to write norm equals true. And we define xmin, xmax. These two lines of code are exactly the same as up here. And then we set the x limits and the x label and the y label. And then we can look at the comparison here, and you can see that the normal distribution does fit the histogram quite well. So therefore, we know that the central limit theorem works. And despite a binomial distribution that doesn't look normal at all, with a large enough sample size, by the central limit theorem, a non-normal distribution will approximate a normal distribution. So in the description, there are links to several other helpful videos, and also links to the code used in this video, and code used to demonstrate the central limit theorem for a few other distributions. And thanks for watching.